want to extend my heartiest congratulations to the dedicated men and women of NASA's Ames Research Center on the occasion of your 65th birthday. Beginning with Ames's pivotal role in aeronautics research, when your founding staff made significant contributions to freedom's victory in World War II, and continuing to the present day, Ames has always played a pioneering role in advancing our nation's science and technology objectives. The Ames team should take great pride in the fact that the first human-made object to leave our solar system, the Pioneer spacecraft, was designed and managed at Ames. The same can be said for the first experiments to look for life on another planet, the Made at Ames science package on the Viking Mars lander, the blunt body concept for spacecraft design, tilt-rotor aircraft, the Galileo Jupiter entry probe, and the water-searching lunar prospector mission are also products of this great center. While the entire NASA organization is currently undergoing an important transformation to meet the goals of the vision for space exploration, it's important to note that Ames has already played a very strong role and has a strong head start in this process. 10 years ago, you began focusing on exciting and relevant technology challenges. Today, these challenges are integral to the way we're conducting this vision. We have so much to look forward to from Ames in the years ahead. In astrobiology, Ames is leading the search for life outside our home planet in whatever form it may take. We look forward to the Kepler Science Telescope's mission to search for Earth-like planets in our galactic neighborhood. We hold great promise for your pursuit of innovative new information science and nanotechnology applications for exploration. And Ames's development of productive new collaborations with industry and academia through the Research Park and the University-affiliated Research Center, we are certain are going to pay dividends for years and years to come. I want to congratulate Scott Hubbard and the entire Ames research team for your uncompromised commitment to excellence and unbridled joy in the pursuit of knowledge that is benefiting all of mankind. Our country looks forward to even more achievements from a research center that is truly a national treasure in an agency that clearly is benefiting by your great contributions. Happy birthday to the Ames team.
The NACA was formed by act of Congress in mid-1915. The acronym stood for National Advisory Committee for Aeronautics. Its original purpose was to advise the U.S. government on matters pertaining to the development of aeronautics. The NACA went on to do a number of notable things. The most prominent were the development of the world's first pressurized wind tunnel at Langley Field in the mid-1920s. They went then in the 1930s on to develop the famous NACA cowling. Also, they went on to conceive of the idea and work out the details of the laminar flow airfoil. Those all became highly used in the aircraft industry. During the Depression, the Great Depression, money was hard to come by. The load on the Langley Laboratory was becoming considerable.
The NACA laboratory at Langley Field in Virginia was overbuilt. There was no room on the tarmac for flight research aircraft. There was no room for wind tunnels. Most importantly, there was no electricity available to drive any new wind tunnels that could be constructed there.
We are on the verge of war, for which we are still unprepared. The American Army has only a few hundred thoroughly modern bombers and fighters. Less, in fact, than Germany is able to produce in a single month.
Trips were made to Germany by George Lewis, the director of NACA, and Charles Lindbergh, to see what was going on in Germany. What they did see really opened their eyes. Germany was far ahead of the United States in aeronautical research. It seems to have been a growing consensus among the military in particular, also the NACA, and some growing feeling in the Congress that something needed to be done.
A, our only laboratory is on the East Coast. B, the aircraft industry is moving to the West Coast. We ought to establish a second laboratory. A site selection committee was formed under Colonel Lindbergh.
The NACA itself finally came up with a proposal to put a laboratory near Sunnyvale, California. The final act of Congress to fund the new laboratory here at Sunnyvale was in June of 1939.
Why Moffett Field? It was located on the West Coast, close to the West Coast aircraft manufacturers in Los Angeles and Seattle. And probably most importantly, there was a craft tradition in the Bay Area. This came in very handy when Ames had to build huge wind tunnel hulls or very tiny electrodes that served for very sensitive instrumentation. Joseph Sweetman Ames was professor of physics and later president of the Johns Hopkins University in Baltimore. Was also a founding member of the NACA in 1915 and served as the chairman of its main committee from 1927 till 1937. And because of the integrity and the trust that people in Congress and in the executive branch of the government had placed in Joseph Sweetman Ames, the laboratory here was established, and in 1944, it was named after him.
A lot of the work during the war years was documenting handling qualities of all the military aircraft they could lay their hands on.
We tested over 56 different types of aircraft just during World War II.
They built the 40 by 80. An airplane has rail guides for its flaps. It has porous spoilers they use for dive brakes. And you put all of that stuff full scale into the wind tunnel.
The war effort and the war itself, of course, dominated everything that was done in research. Now, all this work then was trying to decide what was really needed when you developed a new aircraft. Right after World War II, the big point of interest was to improve the flight behavior when you had shock waves form on the aircraft. Big emphasis was on getting, of course, through the sonic barrier.
We developed a system called wing flow, in which you could mount model airplanes with a recording device in the wing, and with the supersonic airflow over the wing, we'd dive to 0.7, 0.75 Mach number.
Couldn't be in a better environment. There was Al Eggers, down the hall was Harvey Allen, next door was R.T. Jones, Charlie Hall was upstairs.
R.T. Jones, he said that if you want to fly faster than the speed of sound, you should sweep the wing. Tests showed that it was true.
In the 50s, wing sweep came along.
R.T. Jones and Harvard Lomax derived analytical models so that they would be maximum efficiency at speeds other than Mach number 1. In the early 50s, these were essentially adopted by industry nationwide, and that's why airplanes today can fly across country and do these really efficient things.
We did much of the early development of flight simulation from the most rudimentary simulators, a control stick, a throttle, and a TV screen. There were a lot of grumbling at times because the early simulators left so much to your imagination.
Cooper was the man who developed the Cooper-Harper handling quality scale. That is perhaps in our business one of the most enduring products of Ames Research over the years.
Ames, as I remember, the emphasis was focusing on fundamental research to improve the heat protection of entry vehicles. And that involved the special tunnels we had developed here, counteracting a gas gun with a high-speed flow.
About the same time that the transonic wind tunnel was invented, Al Eggers and Harvey Allen came up with the concept of a blunt body. In other words, a very short vehicle, and the blunt surface served as a heat shield. So the vehicle had to absorb very little heat on a re-entry as compared with a long, slender one. I mean, it was just a revolution.
An important period, and its results occurred with the Russians launching Sputnik. That put NACA and the United States government on the spot. We can't afford the Russians to put up even a grapefruit before we put up something. It was decided that NACA's research base was the logical foundation for a space agency. So NACA became NASA in 1958.
That will result in the establishment of a new agency, the National Aeronautics and Space Agency, built around the present NACA, with responsibilities for the non-military aspects of space activities.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I'm going to step off the limb now. It's one small step for man, one giant leap for mankind.
Then when you step into the 60s and we became the space agency, all of physics was open to us. We started a space science group, we started a life science group. There was almost no limit. If you wanted to do something, and if it sounded halfway reasonable, you could do it.
In Building 210, there was actually an Apollo mid-core simulator. And there, what they evaluated was a star field. And also, what they did there was they worked on guidance and navigation systems.
Woody Cook was an early arrival at Ames. And if you had to remember Woody for anything, it would be the fact that he started and evolved all the VSTOL research aircraft work that we ever did at Ames.
When Neil Armstrong was headed for the moon, he actually practiced moon landings in the XV-14, which was kind of a milestone for us.
Well, in the early 60s when I came here, it was, in my view, a difficult job to sell the agency on the idea that they needed to have an in-house life science research capability.
We really didn't know what the risks were, what the hazards were, what the long-term effects of spaceflight were on living systems.
The 60s were a time to get organized, to get ready, to bring in good people, to get our laboratories going, and to establish some kind of reputation as serious researchers.
Well, at that time, life sciences was going hot and heavy. Origin of life was a biggie. You know, how did life originate on the Earth? Also, we had a project called the Biosatellite Project. Now, that was the first real attempt to get science information from microgravity flight experiments.
At that time, the country was trying to build a supersonic transport, at least to do some research and build some prototypes. So by trying to study the flow fields about these vehicles, trying to compute the sonic booms and their propagation to the ground was a very interesting and challenging problem.
In the 1960s, Ames began to launch its first space probes, the early pioneers, to begin to study the conditions in interplanetary space. Ames scientists were among those who first began to explore the Jovian system and got the first spacecraft view of the planet and its satellites.
Charlie Hall was a remarkable research person at Ames. He started out in the wind tunnels. He was good at project management even in those days, and he was chosen by Al Eggers to look at a solar probe. The solar probe developed into the Pioneer Project, which was one of the most successful that NASA has undertaken.
Post-Apollo era, when NASA suddenly was set adrift, didn't quite understand its place within the national research culture, that Ames suddenly had a lingering NACA culture that allowed it to address the development of tools to solve new sorts of problems.
The 1970s really saw heavy activity in the project aircraft area, which initially focused on STOL aircraft and then moved into the VSTOL arena. So the rotorcraft work got underway very heavily and has continued to today until it is the remaining flight research activity.
The VMS, the Vertical Motion Simulator, is the world's largest motion-based simulator. It's actually a very high fidelity, large motion platform which gives very high realism for the pilot. So they actually get the motion cues as if they were flying the real aircraft.
The mission to Planet Earth, the idea of looking at Earth, of sensing Earth, of addressing questions of pollution and agriculture, development in the Third World. Now, it made a lot of sense to bring that sort of work here to Ames. And Ames did very well in defining new sorts of tools to put on the airborne science aircraft that it got here beginning in the 1960s and continuing up to the early 1990s.
I think Viking was a tremendous shot in the arm for the robotic space program. I mean, the fact that we went there, we sat there for several years doing all kinds of experiments, came away with tons of data which are still being analyzed, I think showed the world that serious science could be done on another planet.
A very interesting person came here by the name of Dr. John Parker, and he was very good at generating foams. That was the forerunner and the precursor and the research that led to our present heat shield technology. Like on the shuttle, it has a special heat shield material that was developed here at Ames Research Center.
Probably the most publicized event in the airborne science program was the ER-2, or Very High Altitude program. Its biggest claim to fame was the fact that it actually flew through the ozone hole that was developing over Antarctica. As you know, that data ultimately ended up in what they call the Montreal Accord and changed the law of the land to make CFCs illegal to use. Then we had the Kuiper C-141 aircraft, which was the first airplane to have an infrared telescope.
Also during the 80s, in an effort to consolidate the agency's flight research activities, Dryden Flight Research Center became a part of Ames, enhancing the expertise of both centers. Then during the early 90s, Dryden again became an independent research center.
Ames was a leader in the computational fluid dynamics arena, and they were recognized world-class by all of the people around the world. We were able to compute flows about some problems that I could never conceive having applied this discipline to, such as the entire Space Shuttle launch complex that consisted not only of the shuttle orbiter, but of the external tank and the SRBs in a launch mode. Some of the aircraft that Boeing has built most recently utilized quite highly some of the computational fluid dynamics codes that were developed here at NASA Ames, and those codes have been most recently used in the design of the Boeing 777. Using computer graphics for data reduction led to the development of SGI, silicon graphics.
The work starting in the mid-80s, it centered on the YAV-8B Harrier modified into a fly-by-wire control research platform, has seen its primary application to current-day developments in the Joint Strike Fighter program.
The 90s was a decade of good times and bad times. Some of the aeronautics research work was winding down in terms of the support from Congress. Mr. Golden gave Ames some new challenges in terms of information sciences, information technology, and even later in the decades, the challenge of instituting an astrobiology effort here at Ames.
Our intelligent advisor concept is being utilized in the air traffic management system research that we're performing here at Ames. Using this, the FAA is incorporating it into the air traffic management system for the entire United States. And the future is even brighter still, where we'll be utilizing these concepts to create a safer system that can handle the anticipated increase in the capacity for the new millennium.
One of the major accomplishments that occurred in the discipline of computational fluid dynamics was when we declared success on accomplishing our vision of the numerical wind tunnel. We were able to simulate flows about the F-18 aircraft at a high angle of attack in which you have vortex shedding and vortex bursting, and those vortices intersecting the vertical stabilizers on the F-18.
We've had two really delightful experiences with planetary exploration in the 90s. The Galileo probe, which sent its spacecraft into the atmosphere of Jupiter, was the most demanding entry probe ever flown by anyone, and it worked perfectly. Then later in the 1990s, Lunar Prospector was the first true, smaller, faster, better, cheaper mission, a low-cost planetary mission that showed that we could still do really first-class engineering and show how a mission could be done for less cost and in less time than ever before. Ames in the 1990s has a very special role in space science. The expansion of our traditional study of exobiology, the origin of life, into the new field of astrobiology, which looks at the origin, evolution, distribution, and destiny of life in the universe. So we have studied comets and asteroids and meteorites and begin to piece together the steps by which life originated on the Earth and perhaps on Mars and elsewhere.
In the early 90s, in a span of about 4 to 5 years, we flew 4 major Space Lab missions with over 60 experiments, great science success, great engineering development, proof of concepts.
In the last 10 years, NASA Ames has transformed itself into a research and development center for the 21st century. Our science and our technology systems will enable the vision for space exploration. Our discoveries and our innovation will provide solutions to the very tough problems that we will face as we explore space. What we need to do to enable the exploration vision is to establish greater capability at smaller mass and hopefully smaller cost. Our unique capability here in nanotechnology is something that we will be counting on for the future. We're going to have the capability to model and simulate. That will use our high-end computing. We will need the ability to operate autonomously on other planets. That's our human factors and our human-centered computing capability. Our scientists and our capability in astrobiology will provide the scientific heart of the exploration vision. Every vehicle that comes in the future will need to have a thermal protection system, whether it's going into the atmosphere of Mars or returning from the Moon to Earth. We will play a critical role in defining those new materials and in using our facilities here to test them. We will more and more rely on innovative alliances and innovative collaborations. We've already established that here in developing the NASA Research Park. We have entrepreneurs, we have major universities, we have major companies all locating here so they can work together with us to advance the mission of NASA.
The thing that's always been impressive about Ames are the people that were here.
I think the director and the head of personnel just has to be psychic in identifying people. But it takes a few, 1 out of 10, 1 out of 20, inspired people. When they get an idea, you can trust them to try it.
If the one lesson I ever learned in my 52 years, it's the people. There's some outstanding people here and still are.
Ames people, Ames scientists, using the language of science, has written the poetry of the stars.
As we celebrate Ames' 65th birthday, we have a great deal to be thankful for. We have an extraordinary past. We have a very bright future. We have 2 new powerful tools that are going to enable the vision for space exploration. One is SOFIA, our airborne observatory that's going to penetrate the depths of the infrared universe. The other is Project Columbia, the world's fastest operational supercomputer. It will be used to design new vehicles, to understand data from space science, to calculate global climate change. All of this is part of the new Ames, the Ames that's grounded in Silicon Valley, taking advantage of the extraordinary intellectual capital that we have here with our partners in universities and industry and in other government centers. All of this is going to lead us into the future, supporting the vision for space exploration enabling NASA's missions through astrobiology and unparalleled technology. We are going to explore space together.
Congratulations to our Ames colleagues on the occasion of the 65th anniversary of the Ames Research Center. Happy birthday. At this great organization we know and love as NASA, you all play a pivotal role in our efforts to attain the next big objective of exploration. Keep up the great work.